Hello everybody, welcome to the 10.2 part 2 video, which we are starting to focus on the relationships again between logarithms and exponents, focusing on evaluating logarithms and making connections about how you can convert between exponents and logs. So if we start to look at this definition here that we already know, we know that an exponential function is something like y equals b to the x. So in a numerical way, we can think of it as something again we know, 25 equals 5 squared, or 5 squared equals 25. Now, the reason that logarithm functions were created is because exponentials and logs are inverses of each other. And if I go back really quickly to the previous video, I'm going to focus on this first problem we did, that we tried to find the inverse here, but we did not have a way to, after we switched x and y, to resolve for y. So mathematicians created logarithms to be the inverse of an exponent. And so that is why this notation was created. But other than the fact that they are inverses, something else that you're going to hear me say pretty constantly is the phrase logs are exponents. So when you see a logarithm, you are really finding an exponent. So if we look at the definition of a logarithm, log base b of y is equal to x. But because logs are equal to exponents, your answer to a log is an exponent or a power. So if you're given something like log base 3 of 9, you are finding an exponent as your answer. So to show you the relationship between something we know and something we're less familiar with, 5 squared equals 25. So if you're thinking in terms of logs, this is your exponent. Your exponent of 2 is equal to log base 5 of 25. So what this really means is 5 to the what equals 25? Well, we know that 5 squared equals 25. And so this is just a nice conversion, again, so we can do inverses. And I think this will start to make more sense once we go into actual examples. So let me show you some down here. Use the definition to evaluate the following. Evaluate log base 4 of x if x is 16. So we're trying to find log base 4 of 16. And remember, whenever you see a log, this is really the same as an exponent. So my final answer has to be a single number that is an exponent. What we can do is think about this backwards. We don't know the exponent, but we do know that this says log base 4. And in the exponent world, we write the base as 4. I don't know what the exponent is, so I'm going to put a box there, but I do know that it needs to equal 16. And so if we think backwards, 4 to the what power equals 16? Why, that's 2. So that means that log base 4 of 16, the answer is 2, because that's the exponent that makes it true. The next example, log base 2 of x if x is 64. So log base 2 of 64. So log base 2, I know that the base is 2. I don't know what the exponent is yet, but I know that a log is an exponent. So 2 to the what is 64. Well, if I multiply 2 by itself 6 times, 2 to the 6th power, that's going to give me 64, which means that my answer, log base 2 of 64, is the exponent of 6. So my answer is a single number. If I take a look at the third example, this is really log base 5 of 1. Base 5, I don't know what the exponent is, but I know it equals 1. If we think back to exponent rules, any base to a particular power always equals 1. Well, any base to the 0th power equals 1. So my logarithm, or my exponent answer, is 0. Last example in this grouping, we want to find log base 3 of 1 over 81. Well, as soon as we have a fraction, that can be a little confusing, but you might recall from previous videos that reciprocals or fractions come from negative exponents. So let's think this through. I know that 3 to the 4th is 81. So it would make sense to me that 3 to the negative 4th equals 1 over 81. And so if we use the same logic here, again, logs are exponents. We're trying to find the exponent that makes this true. So 3 to the what equals 1 over 81? Well, based on my logic over here, it is my negative exponent of negative 4. So my answer is negative 4 for that fourth example. Write the logarithmic equation as an exponential equation and solve for y. So again, we're practicing the idea of converting from logs to exponents so we can use this eventually to solve equations. So logs are equal to exponents. So that means in this example, my exponent is my unknown y. I know that this is log base 2, so 2 to the y equals 16. Some of you might be able to solve this without doing any work. You might say that I know that 2 to the 4th is 16. If it helps though, what we can do is change both of these to be 2 to a power. This side is 2 to the y, and some of you might recognize you can take 16 and convert that to 2 to the 4th. If you have the same base on both sides, that means that the two exponents have to be equal. So either way, we get the answer that y equals 4. Part 2 here. The exponent again is y because logs equal exponents. So my base is 2. I'm raising it to the y power. We want to know how that can equal 1/2. So again, we could just look at it and guess what y is, or we can convert both sides to be the same base. We can leave this one as 2 to the y, and then this one we can think about how to rewrite 1/2 as 2 to a power. Well, if 2 to the first is 2, it would make sense that 2 to the negative first is 1/2 because it causes a reciprocal. If both sides have the same base, the exponents are equal, so y equals negative 1. The third example, this time we know what the exponent is, it's 5, but we don't know what the base is. So we'd have y to the 5th equals 17, and then we'd still have to solve for y. So let's think of our previous knowledge here. The easiest way, in my opinion, to get rid of a y to the 5th is to take a 5th root of both sides, which makes sense based on square roots and cube roots, which we've covered already. So if you wanted to leave your answer exact, these would cancel because they are inverses. You would have y equals the 5th root of 17. So a lot of this leads to general properties of logs, which will continue to help us later. If we think about what log base b of 1 means, that means, because again, we're trying to find exponents here, b to the what equals 1. Well, the reason this is a property is it's always true. Any base to the 0th power gives me 1. So log base b of 1 is always 0. Log base b of b. So this really means b to the what is the same thing. Well, if I raise any base to the 1st power, that's equal to itself. So this answer is always 1. Log base b of b to the x. What this really means is b to the what equals b to the x. Because again, we're trying to find the exponent over here. We don't know it. B to the what equals b to the x? Well, just like the problems above, if the bases are the same, the exponents are equal. So this also has to be x. And also something to point out is log base b and b are inverses of each other, so they technically do cross out and you're just left with x. Which leads me to this example, b to the log base b of x. These are inverses. So if I take an exponent and raise the log, because exponents and logs are inverses, they cross out and you're really just left with x. Same thing here technically. And the last rule that we've used a decent amount so far in terms of exponents, it makes sense to me that because logs are exponents, that just like up here, if you have the same base on both sides, that means that the exponents have to be equal. So that means that if you have log base b on both sides, that means that the argument, or what log base b of x equals log base b of y, then x must be equal to y in order to go with the rule that we already used with exponents. To transition to using logs on your calculator, is there a log that is perhaps, or that does appear, more often or is more useful than other logs? Well, if you think about past classes, or if you look at your calculator, there is one that is very, very popular, and it's log base 10. Every calculator has a log button, but something you need to know is just like when you take a square root of x, we don't really write that as with the little 2 there. We assume that it's really square root of x. In a similar way, when you're doing log base 10, it's tempting to write it like this, log base 10 of x. But what your calculator does, and what the assumption is that this common base is really just written as log, or log of x. So whenever you see log of x written, you really assume there's a secret little 10 down there, log base 10, but you don't have to write it. Which leads me to the last problems in this video. Evaluate using your calculator. I think it's important, of course, to understand where logs come from, but sometimes, unlike the previous examples, we don't have exponents that are perfect, so we need to know how to use our calculator. All right. So before I pull up my calculator, I'm going to rewrite all these problems without the base 10. So this is really log of 2/5. This is really log of 5. And this is really log of -4. And the 10 is assumed. And the reason that this is so handy is if I pull up a TI calculator here, there is a lovely log button right here underneath the x squared. And so we can find any logarithm answer as a decimal easily. So for the first one, if we pressed log and then the parenthesis, I'm going to put a parenthesis in and write 2/5 and then press enter. Hopefully I can do that here. I got the answer of -3.9 or -0.3979. That's what I'm going to write here. This log is not perfect, and here's why. Let me write the answer down first. 0.3979 negative. The reason the answer is not perfect is if you think of this through, if there's really a base 10 here, and you're trying to find the exponent, you have base 10 to the what equals 2/5. Now, 10 to the first is 10. 10 to the 0th is 1. 10 to the -1st is 1/10. 10 to the -2nd is 1/100th. So we do not have a perfect exponent or an integer coefficient exponent. So that's why my answer is a decimal. This next one, before we find the calculator, what we're really trying to find is base 10 to the what equals 5. And it's tempting. It looks like there should be a relationship here. But 10 to the first is 10, and then 10 to the 0th is 1. So we skip right over 5. So that's why we have the calculator. So if I clear, and then again go with log of 5, my exponent answer is 0.6989. So we'd have 0.69897. And lastly, this example, log of -4. Now this one's interesting because we have 10, base 10 to the what equals a negative number. Now even without a calculator, let's think this through. Has there ever been a situation that we've had a power to an exponent equal a negative number? Because let's again think about the power of 10. 10 to the first is 10. 10 to the 0th is 1. 10 to the -1st is 1/10. 10 to the -2nd is 1/100 because that's 10 squared and the reciprocal. So literally, there's never any kind of exponent I can plug in that causes a negative number. So this answer would be none. There is no exponent that makes this true. But if we'd like to make sure, we could plug it in our calculator and say log of -4, and it says non-real answer. So our answer isn't real, it's not possible based on the definition of an exponent and a log. So that would be my final answer, none. I'm even going to write a note, not real. So a thought I'd like to leave you with before we end the video here is two examples converting the other direction. If I give you a logarithm, we can change this to exponential form. The base of this logarithm is 3, the exponent is 2, and it equals 9. So this would be the answer written as an exponent. In the next example, the base is 6, it's equal to the exponent of -2, and that equals 1 over 36.